Good morning. Today we shall talk about a few common binary alloys. So far, while discussing phase equilibria or phase diagram, we looked at uh, uh, mostly hypothetical metallic systems. Now, today first I think we will look at rules governing solubility in solid state. We will look at common isomorphous system, common binary eutectics, and we will see when we look at some of the phase diagrams, there are a number of intermediate phases and compounds often we come across, and why do they come, and do they follow some specific rules. And we will also in the process we will learn about few common binary alloys which are of commercial interest. Now, the rules that govern the solubility limit is known as Hume-Rotary rule. Now, the factors which are listed here, one of the most important factor is size factor. If the atomic diameter of two metals are within plus minus 15%, then we find that they have very large solubility. They can have, provided few other conditions are met, like one is they must have identical crystal structure, they must have same valency, they must have nearly or close electronegativity values, that is within 0.4 electrostatic units in that Pauling scale. And we have seen that metals that satisfy that Hume-Rotary rule, they have unlimited solubility in solid state, and some of the examples I think one we looked at is a copper nickel alloy. So, another example is silicon germanium. Now, what happens if there is deviation from non-ideality? That means, if the size factor, say suppose the two metals A and B, they have same crystal structure, that is same crystal structure, but say in case where you have the atomic diameter are within plus minus 15%, you get this kind of a diagram. This is liquid, this is solid, this is alpha. You have unlimited solubility here, and in this case the properties also we have seen, they will vary like this. Somewhere in between you will have the maximum strength. Now, what happens if the sizes are slightly different? In that case it starts, we get deviation from ideality, and this is like this. Say maybe it shows a minimum here, still it has solubility. Say this is liquid, and you also can have say this, and this is alpha. If the size factor differs little more, then you can have some amount of cluster formation, and you may have this kind of miscibility gap alpha and alpha 2 forming. But both here alpha entire stage, alpha 1 also has same crystal structure. If alpha 1 is FCC, alpha 2 is also FCC. Now, if this deviation goes on increasing, then what happens? Finally, you will land up with eutectic say this is alpha, this is beta, this is liquid. Now, Here what you have, if you look at that nearest neighbor, if it is an isomorphous system, that number of nearest neighbor or AA bond, number of AA bond will be equal to, say, if the alloy contains say an 90% A, or let us say more somewhere in between, let us say 50% A and 50% B. In that case, this AA bond, if it is face centered cubic, the coordination number is 12. So, that means each A atom will be surrounded by 6 A atom and 6 B atom and 6 A atom. There is no preferential arrangement. Now, if this kind of clustering forms, then what will happen is number of AA bond will increase. That means, instead of say 6 A atom, it may have 9 A atom or even more surrounding an A atom. Similarly, each B atom may be 9 or 10 B atoms surrounding it. So, that way a cluster forms and ultimately it leads to an eutectic type of phase diagram. And this is what is shown over here, that condition for isomorphous system is that AB type of bond will be equal to the average of number AA plus NB over 2. So, this will exactly match with the atom fractions, that nearest neighbor, that or number of AB type of bond will be that given exactly by the atom fraction or the composition of the alloy. Now, when a eutectic forms, then what happens? The AA bond or like bonds will be more in number. So, that means AB type of bond will be less than what is expected from the composition. Then you get eutectic type of structure, and in other case that we can also have a case where number of AB bond is more than that given by the composition over here. In that case, there will be tendency to form compound, and depending on the deviation, extent of deviation, we can have different types of phase diagram. Now, we shall look at few examples. Now, copper nickel, it forms a isomorphous system. It is soluble in all proportion in both liquid and solid state, and if you look at their crystal structure, both are face centered cubic. This is the atomic the lattice parameter 3.61 angstrom, 3.52 angstrom. So, the difference is not much. Their electronegativity, there you look at their atomic number, they are very close. So, therefore, electronegativity is also very close. So, therefore, they form an isomorphous system. This type of alloy is very common, one of the commonly used alloy. It has good strength, ductility, and in this alloy, this is how the tensile strength will vary, and whenever tensile strength goes up, you will find the ductility of the material goes down. You will have something like this, and some of these common applications which are listed here. This material, apart from strength and ductility combination, it has low temperature coefficient for resistance, and it has good corrosion resistance. So, therefore, it is used for a number of marine applications like heat exchanger, condenser tube. It is also used as thermocouple. The copper constantan, that thermocouple, that constantan is made up of copper, 46% nickel. Now, germanium silicon also forms a isomorphous system. So, these are the melting points. This diagram is, mind you, is schematic, and both germanium and silicon, they have diamond cubic structure. Look at their atomic look at their lattice parameter. This is 5.66 angstrom. 1 angstrom means 10 to the power minus 8 centimeter or minus 10 meter. So, the and diamond cubic structure is 5 for the silicon it has 5.43 angstrom. Both belong to group 4 of the periodic table and their atomic numbers are 32, 14, and in fact, their electronegativity is also not very much different. So, that is why you get this kind of a unlimited solubility. Now, let us look at another case where there is a slight deviations from in their size factor, like copper gold system. Copper gold system, see high temperature it has a isomorphous system here, it shows a minimum somewhere in between, and down below you will see there are now some changes you do see when you go down to at lower temperature, where the deviations effect shows up, and here particularly look at the central region. So, here some kind of ordered structure formation is taking place, some kind of an ordering, say like atom unlike atoms like gold copper. Gold prefers to have more number of copper as its neighbor, say something like this here. So, therefore, we say that in ordered structure something develops, and all this follows from because there is a deviation from ideality. If you look at their atomic lattice parameter, there is a slightly large, a little more differences there. Look at their atomic number, there is a large difference in their atomic number. So, obviously, their atomic diameter will be slightly different. I mean may not be within that 15% limit, and here this kind of tendency shows up, like here this is a structure, both has face centered cubic structure. So, you have atoms both have you have atoms at the corner of the cube and each of the face centered. Each of the face centered. So, there are 6 faces. So, 6 face centered atom and there are 8 corners atoms. Now, but these atoms they do not belong solely to this unit cell, and we know that face centered cubic structure there are 4 atoms per unit cell, and here when this kind of ordering takes place, what happens is gold and copper atom will occupy specific sites, like here one atom will occupy, one of these will occupy each of these corner sites and these sides, and that the base also. So, if you count, so there is one corner atom and one face center atom. So, therefore, 2 atoms as let us say is gold, and let us say this sites face centered, that 4 face centered atom is the second atom copper. So, this also is 2. So, they are in this ratio. Similarly, if you look at here, here also a similar kind of rearrangement takes place. Here all gold atom will occupy the corner atoms, corner sites. So, gold goes to corner site and copper atom face center sites. So, there are 3 face centers and 1 corner site. So, they are in ratio 3:1, which represents the composition. Likewise, there is a possibility you can have similar ordered structure here also. So, ordering in a way you can say that this has a tendency to form a compound, where unlike bonds are more than the normally expected in a random solid solution. Next, let us take up a case of an eutectic. So, this is lead tin, which is a common alloy which is used as a solder because of its low melting point, because it forms eutectic. Each of these metal, they are low melting metal. Tin has a melting point 232, lead has 327 degree centigrade as its melting point, eutectic melts at 183, and the solder composition is close to the eutectic composition. And here if you look at the crystal structure, why do you get an eutectic here? One is, look at, there is a difference in crystal structure. So, the unlimited solubility in solid state is ruled out. Tin is tetragonal, this is the lattice parameter A, this is the lattice parameter C, lead is face centered cubic, its lattice parameter is 4.95 angstrom, atomic numbers 50 and 82, but both belong to the same group of periodic table, group 4 of the periodic table. Another common eutectic which is of commercial importance is aluminium silicon. Aluminium silicon is a good cast alloy, and many of these components, engine components are made of aluminium silicon eutectic. So, look at this is an high, I mean not to scale, but this eutectic temperature is correct 577. This is the melting point of silicon, this is the melting point of aluminium, and eutectic composition is around 11% silicon. This 11% is a weight percent, atomic percent will be little different. Now, look at this crystal structure, they are different. This is face centered cubic, atomic number 13, it is a its valency is 3. So, I think it should be 3, group 3 element aluminium. This is soft and ductile, whereas silicon is cubic, its lattice parameter is 5.43, atomic number 14, it is a group 4A element, it is hard and brittle. So, in the alloy if you have more amount of silicon, then it becomes brittle and it is not of much practical use. So, therefore, if you want a good alloy with a good strength as well as ductility, then one way could be you modify the structure such that you can take in that eutectic can have more than what is predicted from a normal equilibrium diagram, and this is where some tricks are played. If you add something additionally or if you cool rapidly, then it is possible to change that structure of the eutectic, and this process is called modification. There are two ways modifications can be done. One is by adding something say like sodium or sodium chloride, if you add to the melt, then the structure gets modified. Say suppose if you look at this alloy composition which is hyper eutectic, say here maybe around 13 or 14% silicon, this composition. So, under equilibrium condition what you expect, it is a silicon plus liquid here. Here you have primary grains of silicon which is brittle, plus you will have eutectic which is made up of aluminium plus silicon. Now, if you add sodium, then what happens? Its eutectic composition shifts to the right the temperature also comes down here. So, its fluidity increases. So, it is more easy to cast, and this drop may be about 20 to 30 degree centigrade. It may drop by 20 to 30 degree centigrade, and it can have more amount of silicon in the eutectic, and silicon in eutectic they are relatively fine. So, therefore, its properties will be improved, strength will be improved, ductility will not be hampered, and it is a very useful cast alloy. Some of the components which are made of aluminium silicon, they are listed here, and sometime few other alloying elements are also added to improve its properties. The modification is also possible by relatively faster cooling. If you cool it faster, then also the eutectic will shift. So, also the eutectic temperature comes down. So, this is another example of a lead antimony eutectic. This also has a limited solubility, and if you look at this lead face centered cubic, antimony is rhombohedric, and then lead atomic number is 82, antimony is 51, and they belong to different groups of periodic table. And here also the properties will vary something like this. In most cases, in cases where the second element, there are two ways this properties can vary. If say like here, if eutectic is very fine, you may find the property improves, strength improves up to this part, and antimony lead is relatively softer, antimony is brittle. So, therefore, this part the strength, although it increases, the rate is not at the same level. Similarly, its ductility will also come down. The ductility, say suppose it comes down like this. Nickel chromium is another good example. It is the nichrome heating elements are made up of nickel chromium, around say somewhere 80% around this composition is the nichrome, and it is a common heating element. Look at their crystal structure, they are different, their atomic numbers they are nearby, chromium 24, nickel 28, and nickel is magnetic. So, here you have a Curie point, this line represents the magnetic transformation temperature. Nickel, pure nickel is ferromagnetic, but if you add chromium to it, that Curie point comes down, and this side it is no longer magnetic. And in fact, this is the basis alloy based on which super alloy which are being used as gas turbine alloy have been developed. When gas turbine engine came up around the same time as the Second World War, the best material that was available was austenitic stainless steel, and later on they found that if you add that heating elements, a little amount of aluminium, then its high temperature strength increases significantly. So, therefore, life of these turbine blades made up out of these types of alloy, they last longer, and performance of the engine also is better. So, therefore, this formed with this actually the large number of super alloys which have been developed, they are actually based on nickel chromium, that nichrome alloy. The first generation of super alloy is called mnemonic. Now, here is an example of a case where you have some intermediate phase forming. This is gallium, this is arsenic, and you have gallium arsenide. look at their melting points. Gallium melts at around 30 degrees centigrade, whereas arsenic at 1800 around 817 degrees centigrade. But look at this gallium arsenide, melting point increases significantly and its behavior is exactly same as melting. If you plot its cooling curve or solidification curve, it will be freezing curve will be exactly same as that of a pure metal. Like gallium arsenide is a pure metal, sorry, not a, it's a pure, something like gallium arsenide, it's a compound, and if you will plot its cooling curve with time, it will follow of this kind. So, this temperature is 1238. It will appear as if its melting behavior is exactly similar to that of pure metal, and the crystal structure and which are listed here. Gallium is orthorhombic, arsenic is face hexagonal close pack structure, and gallium belongs to group 3A, whereas arsenic belongs to group 5A. Now, another example which is given here is magnesium tin. It also forms a compound, and this compound, look at this, magnesium Mg2Sn. So, Sn means tin belongs to group 4, its valency is 4, Mg belongs to group 2 and its valency is 2. So, therefore, this compound, it is something like a chemical compound, it is very close, similar to a chemical compound that forms, and this also has a behavior congruently melting behavior. So, that means its cooling curve will be exactly similar to that of this pure magnesium or pure tin. Now, let us look at a very common alloy, brass. This is amongst the first alloys which have been used by mankind, and both have, if you alloy copper with zinc, its melting point decreases, it will be easier to make. And look at this diagram, apparently it looks rather complex. Now, copper, it has a face centered cubic crystal structure. This is the lattice parameter 3.61, its atomic number is 29, it belongs to group 1B. Zinc, it has hexagonal close pack structure, these are the lattice parameter, this is A, this is C, its atomic number 30, it belongs to group 2B, its valency is 2. So, what you find here, several intermediate phase, like one here is a beta and here there is a beta prime. So, if you cool below a particular temperature, the beta also has a composition somewhere close to around 50 atomic percent zinc. So, there are copper and zinc atoms, they are present in 1:1 ratio, and its crystal structure is body centered cubic, alpha is face centered cubic, and when this ordering takes place, one of the atom will occupy the corner site, another atom will occupy the body center site. So, that is what ordering is in this particular case. You add more zinc, you get another intermediate phase gamma, you add even more, you get another intermediate phase which is called epsilon, and ultimately the terminal solid solution, zinc rich solution, which is eta. So, you have several intermediate phases in between, and amongst brass, the common brass which is used, which is known as alpha brass, and here if you look at the properties, mechanical properties of brass, as you add zinc, you will find that UTS, it goes on increasing somewhere something like this, and somewhere here it becomes maximum and then it drops down, and elongation ductility also increases up to a certain point and then it drops down, and you get an optimum property around 30% of zinc. So, therefore, 30% 70 copper 30 zinc is a common alpha brass, and it has several, it is also known as cartridge brass, which is used for making cartridges. And another important cast alloy is a 60-40 brass. 60-40 brass, which will be, if you look at that phase diagram, 40% zinc will be somewhere here. So, where the structure will be 60-40 brass, it is yellow in color, is yellow, it is called alpha beta brass. And 70-30 brass, it is a single phase, it is called alpha brass. Now, this can be cold work, whereas this, since it has two phases, it will be difficult to cold work. It can be worked, if you have to work it, you have to heat it to the beta range. So, this phase diagram also tells you not only about the microstructure, you can infer properties, you can find out the temperature range where it can be worked. And one interesting alloy which is here, which is shown by this line. This alloy, if you heat it, here it is single phase, here it is beta. But when you cool it slowly, here from some amount of alpha will precipitate out, here sometime it will be mostly alpha and again beta starts precipitating out. But if you quench it rapidly, you do not allow this precipitate, then you get a structure where this high temperature thing is retained, and we will later learn about it. This may not have commercial importance, but this is an alloy where you have a transformation, something when we talked about TTT diagram, time temperature transformation diagram, we talked about a phase called martensite, which forms without diffusion. So, here also you have a similar kind of transformation. If you heat this alloy to this range where it is totally beta and then quench. Another very common alloy is bronze, it is a copper tin alloy. This also have been used since ages, and the diagram, look at it, looks quite complicated. It is schematically I have represented. We have not gone up to the full range, we have plotted only up to 45% tin, and look at the number of phases which appear and the number of peritectic. So, if you look at the brass diagram, if you go back to the brass diagram here, if you see that you only have different peritectic reactions and one eutectoid reaction. You have 1, 2, 3, 4 peritectic reaction. Usually you will find in phase diagrams, if the two metals, the melting points, they are widely different, there is a tendency to form peritectic type of systems, and this is an eutectoid system, and you have an order disorder transformation here. Now, in case of this bronze alloy, if you look at, you have a peritectic over here, you have another peritectic here, and then again you have an eutectic here, and you have an eutectoid, you have peritectoid, and it has another eutectoid here. So, you have multiple number of eutectoid and peritectic system, and you have number of these phases. The primary solid solution is alpha, which is phase centered cubic. Then you have beta, which exists only at high temperature. This is the region where beta existing. Then you also have a gamma phase, this also exists at high temperature, but room temperature usually the most stable phase will be epsilon phase. The tin, if at all is present, at room temperature it will be present as Cu3Sn, but this type of precipitation reaction in solid state is very slow, and usually you may find, instead of this you may also find the delta phase retained at room temperature. Now, titanium is of is an alloy which has a great potential, particularly for aerospace kind of application. There is a lot of work which is going on in titanium, and right now its commercial use is limited because of its cost, but it is expected that this cost will come down, and titanium shows an allotropic transformation. At room temperature it is hexagonal, it has a beta structure, it is hexagonal, which these are the lattice parameter of the HCP, but at high temperature it is BCC. So, at a high temperature it will be more easier to work than at room temperature, and intermediate phase also is there. There is a gamma phase, and there may be some intermetallic here phase which is forming. And here if you look at this, this belongs to titanium belongs to group 4b, whereas aluminium belongs to group 3a. And titanium vanadium is another alloy. I think usually it is customary, if I go back the previous one, you change this. High temperature phase is usually beta, the low temperature we call it the closed packed is alpha. So, you make this change here, this high temperature we will of course, this is a custom which people follow, it does not matter, I mean whatever you write, but what it means is a low temperature phase which is a closed pack, usually people represent it as alpha, and high temperature the BCC phase as beta. So, and here it is correctly represented, and if you look at their crystal structure, because crystal structure is different, it cannot have unlimited solubility at all temperatures. So, here that allotropic transformation takes place, this portion is beta, this is the terminal solid solution portion alpha. So, vanadium you can say it stabilizes beta at lower temperature. If you want to bring down the hot working temperature, you may have to add an element like vanadium. There are maybe similar other elements also which will stabilize that beta phase, and this is a typical diagram of a titanium vanadium alloy. And in fact, you can go on like this, there is no end to it, and these handbooks give you the phase diagrams. Metal handbook gives you the phase diagram of different metals, and in fact, there are now computer databases like FactSage. You can go to their site. There are thermodynamic database, in many cases and it gives you, if you log on to their site, you can get any phase diagram, any binary phase diagram, the list of binary phase diagram you can get from this and this thermodynamic database. This is a thermodynamic database, and wherever these are experimental data not available, people refer to thermodynamic databases and construct the phase diagram. Now, what we have seen now, that when you have a real system, you do get several the intermediate phases, and these intermediate phases they have some specific crystal structures also. Now, let us look at what are these intermediate phases little more critically. That intermediate phases can be put into three groups. One is an electrochemical compound, like a chemical compound formation it takes place. It is whenever they belong to different groups in the periodic table, then there may be a tendency, if they are further apart, there may be a tendency to form a compound. like magnesium here, magnesium belongs to group 2, whereas these elements lead, tin, germanium, silicon, they are group 4 and they form a compound, and this is, it is in proportion to their valency Mg2 Si or Mg2 Pb. It is like a chemical compound. Similarly, magnesium arsenide Mg3 arsenic, it belongs to group 5. So, its valency is 3. So, it forms Mg3 As2. Similarly, bismuth antimony can also form a similar compound. And we also talked about a solid solution where the solute element goes to the interstitial sites like carbon, and this also is depends on the size factor. When there is a large difference, say something like say 40% or so, large difference in the atomic sizes, that means carbon atom is so small that it can be accommodated within the interstitial sites of iron lattice. In that case, there is a possibility that a compound may form, and like cementite, that which is Fe3C. This is called size factor compound. This is not necessarily guided by their valency. So, therefore, they derive a different name, size factor compound, and likewise you have another type of intermediate phases which are called electron compound, copper zinc, copper aluminium alloy, Cu9 Al4 or CuZn3. So, look at, although we, I mean they do not come in that order of that valency, does not play. So, this is not necessarily, we cannot say that this is an electrochemical bond that is forming. So, this belongs to another class of intermediate phase. And now, this look at this electrochemical compound. It forms when one is electropositive and the other is electronegative, and we gave these examples that Mg2 any of these, similarly Mg3 and any of these belonging to group 5 elements. So, and these are listed, these are the atomic number and their group are listed. Now, if you go, if these atoms are smaller, we have seen that bond formation, bonds are stronger when this atom size decreases. In that case, atom can come closer. Therefore, this bond Mg2Si, this bond will be much stronger than that in Mg2Pb. So, therefore, what we expect, the stronger bond, higher is the melting point, and which is shown here. If you look at their melting point, this increases as you go up the group, that is silicon Mg2Si has the highest melting point, where Mg2Pb has the lowest melting point. Now, size factor compound is actually formation is primarily guided by the atomic sizes, and here what is important is the ratio of the atomic diameter or atomic radius, like radius of this interstitial atom, radius of the metal atom. If this ratio is between 0.41 to this, you have a tendency to form a compound. If it is even, this ratio is less than this, then it is present as a solid solution. Its crystal structure is the crystal structure of the parent metal, but if it is in this range, then there is a tendency to form a compound, and this compound has interesting crystal combination, either Mx, M is metal and X is the interstitial element, M2X. So, like this, and some examples are carbides and nitrides of titanium carbide, zirconium carbide, hafnium carbide or hafnium nitride, so vanadium nitride, vanadium carbide, and these are some of these examples where this type of structure forms. and here the crystal structure is little simple. It is appears you may find the crystal structure may be very much similar to the crystal structure that you get in sodium chloride. So, in case of Mx, say one will be occupying that means sodium positions, another will occupy the chlorine position. So, this type of structure is rather simple, but with nitrides the structured nitrides are simpler than carbides, and here particularly, but if you look at cementite, here if you look at their atomic diameter or atomic radius, this is greater than this. So, therefore, in this particular case there is more lattice distortion, that means carbon atom is larger than the nitrogen atom. So, when carbon goes into iron lattice, it produces a larger distortion and it results in a more complex crystal structure. Another type of intermediate phase we often talk about, it forms is called Laves phase. This forms when also this is also we can say size factor compound. This forms when the atomic size difference is around 20 to 30%, and it has an interesting structure, say AB2 type of structure, where each A atom has, if you look at this, each A atom has 12 B as its neighbor and 4 A atom as its neighbor, and each B atom has 6 A and 6 B atom as its neighbor, and therefore, average coordination number, in that case each A atom has 16 neighbor, each B atom has 12 neighbor. So, average coordination number is 13.33, which is greater than that of a closed pack structure. In a closed pack structure like face centered cubic or hexagonal, the maximum coordination number that you can have is 12, and here it is possible because you have atoms of two different diameter. So, therefore, the coordination number here can be I mean it is possible in such cases coordination number to be greater than 12. And then common crystal structures which are listed here is one is MgCu2 type of group, that is here also you can say this is an AB2 type of structure, Laves phase, and this is based on a cubic lattice, whereas this is based on an hexagonal lattice MgNi2. This is another group which is based on an hexagonal lattice. Now, apart from this, we also talked about electron compound. What are they? And this denote these they do not follow that rule of that valency, like CuZn, usually this has one valency 1, zinc has valency 2, and this, but they have a, and what people have found out, what has been found out, these types of compounds formed at particular ratios of electron to atom ratio, and which you can possible to calculate. Say suppose you consider copper and zinc. Now, zinc can give 2 electron, copper can spare 1 electron. So, total number of electron is 3, number of electron is 3 and number of atom is 2. So, the ratio here E by A ratio is 3/2. So, it has been found in several cases wherever this kind of relationship is I mean this kind of electron to atom ratio is attained, you get a crystal structure which is very similar to copper zinc crystal structure, which is BCC crystal structure, or we can say this is called beta brass. Structure is same as beta brass, and there are examples, several examples which are given here. CuZn, Cu3Al. Here that valency of aluminium is 3, this is 3 plus 1. You have 4, 3 plus 1, 3 copper atom. So, 3 electron and 1. So, 4 atoms, and you have 3 plus 3 6 electrons. So, 6 by 4, it comes out to be 3 by 2. Look up this case, you can do the similar calculation, you can check here. Here also the electron to atom ratio will be 3 by 2. Now, whenever you have compound formation like this with transition element like nickel aluminum, here when you calculate E by A ratio, you assume the transition elements, the valency is 0. So, in that case you have 3 electrons, this is 0, but this gives 3 electrons. So, total electron is 3 and number of atom is 2. So, this is 3 by 2. In the same way you find that gamma brass type of structure, gamma brass is C5Zn8. If you calculate electron to atom ratio, it will come out to be 21/13, and you get similar ratio in several other cases. They all belong to the class called gamma brass type of structure, and this you get in a particular electron to atom ratio. Likewise, you have another called epsilon brass type of structure. This is E by A ratio is 7 by 3. Some of these examples which are given over here, and here also when you calculate iron is a iron is an transition elements, its valency will be taken as 0. So, when you calculate this, this is zinc is 21, valency is 20, number of atom is 21, and each zinc can give you 2 electrons. So, you have 42 electrons and total number of atom is 21 plus 5, 26. Therefore, the ratio comes out to be 42 by 26, which is same as 21/13. So, therefore, whatever we have seen today is we looked at some common binary alloys, and we also looked at the rules that govern the solid solubility limit. We talked about Hume Rotary rule. We have seen that when we looked at several phase diagrams, in many cases number of intermediate phase formation takes place. We looked at their structures. We also talked about order disorder transformation, and we looked at few common commercial binary alloys. We also, and these alloys, some cases we looked at the interpretation of microstructure and structure property correlation. So, with these we finish this topic, and next class we will begin a new chapter. Thank you very much.